Welcome to part 6 of this series that has looked at integration of different functions. In this video, we're now going to turn our attention to our circular functions like sine and cosine. So we have two formulas now that we're going to show. So the first is that the integral of sine of ax dx is equal to, just be careful here, it's negative 1 on a times cos of ax plus c, where c is that constant of integration that we get. And then we have the integral of cos of ax dx is equal to positive 1 on a times sine of ax plus c. So just be careful, one does have a negative in there and one just has a positive. So keep track of those when you're applying these rules. So our first question is going to look at the integral of sine of 5x dx. So applying this rule, this is going to equal, and we have negative 1 over a gives negative 1 over the coefficient of x, which is 5, times, and sine goes to cos, and it's just going to be cos of 5x, and then we're going to have plus c, which is that constant of integration. So that is the answer to the first question we're looking at here. If we move on to our second question, we're now looking at a definite integral because it has terminals. But our first step is still to calculate that antiderivative. I'm going to put that inside square brackets. So we have 6 times cos of 2x. So when we apply this rule, we're going to have 6 times sine of 2x, but then we're going to divide by 2. So hopefully you follow along when I say that that's equal to 3 times sine of 2x. And we don't need a plus c when we're doing a definite integral, because when we evaluate it between our limits of what was 0 and pi over 8 for this question, we actually do that by doing the antiderivative with the upper terminal substituted in, minus away the antiderivative with the lower terminal substituted in. So we'd essentially add on c here and subtract it away in that next part, so it cancels out. We won't need it as part of this process. So if we do this, this is going to equal, and using brackets where necessary, we're going to have 3 times sine, and we're going to have 2 times x, which becomes 2 times pi over 8. So that becomes just pi over 4. And then we're going to subtract away from that 3 times sine, and we're going to have 2 times the lower terminal substituted in, which is 0. So that's simply sine of 0. And now we just need to remember our exact values for our circular functions. So this is going to be 3 times. And now sine of pi on 4, hopefully you remember, is root 2 over 2. And then we're going to subtract away from that 3 times sine of 0. But sine of 0 is simply 0. So we're just subtracting away 0 over all there. So this answer is going to simplify to 3 root 2 over 2. And that's the answer to the second part of this question. Now over here, we're just going to have a quick look at the graph and try and unpack what that means on our graph. So I've drawn part of the graph of 6 cos of 2x over here. So if I just write that down, this is the graph of y equals 6 times cos of 2x. And I've just drawn part of it down. And the part that we now need to look at is between 0 and pi on 8. So that's the area here. So when we do the integral between 0 and pi on 8 of 6 cos of 2x dx, this value of 3 root 2 over 2 is actually the area of this region. So that area is going to equal 3 root 2 over 2. Now just be careful that that is a case here of where the area is exclusively above the x-axis. So of course there's examples out there where the area, for example a region down here, would be below the x-axis. And in another video we're going to explore how we deal with that. But for this one, and again this isn't the case for every example that we do, but for this one, because the graph was always above the x-axis, then the integral between 0 and pi on 8 happens to represent an area under a curve. And that area, as we said, is 3 root 2 over 2. So I hope that this video has helped. If you need to see any more examples like this, make sure you check out the links and all of that sort of stuff below. And stick around, we're going to have a part 7, which is going to look at the integration of some more complicated functions. So in particular, we're going to look at a process called integration by recognition.